Hey guys, Jake here, coming at you with another math lesson today. Doing it live again this week. Happy Valentine's Day. Hopefully it's a good one for everybody. Today we're going to keep on building on integration by parts. We've been talking about a lot of different integration types of problems lately, especially U substitution and integration by parts problems. Just talking about different integration methods that you're going to need to be familiar with in order to make sure that you can integrate whatever functions you're coming across. And I have touched on integration by parts a bit already in the past few weeks, but I want to go into it a little deeper, just keep giving you some more practice, some more examples with integration by parts. And specifically, I also want to get into what it looks like to use integration by parts for a definite integral. So up to this point, the last few weeks, we've just been doing integration by parts for indefinite integrals. I just want to show you how definite integrals are a little bit different. It is very similar steps, similar process, slightly different formula with just a little bit of an extra step at the end, essentially, to kind of account for the fact that it's a definite integral with bounds rather than just, an indefinite integral. So both the indefinite integral and definite integral integration by parts formulas are on my integral calculus cheat sheet or my calculus 2 study guide. If you want to check that out, there is a link down in the description below and in the pinned comment as well. I did also drop in the live chat a link to that study guide if you want to go grab that. It is available for instant download. So I think it should be a big help for you if you wanted to go grab that for yourself right now. But without further ado, let's go ahead and jump into the examples that I have for you guys here. As always with these live streams, if you do have any questions along the way, please feel free to drop those in the live chat. I'm happy to help address whatever questions I can. Even if it's not on topic of integration by parts, if you got some off-topic question that you've kind of gotten stuck on, throw that in the live chat too. I'm, may not be able to answer any question that you might come up with live, but I'll do my best. And if I need to, I may end up making a video about your question later on. I have done that a couple of times before. So drop whatever questions you have in the comments if you're watching it later. Drop it in the live chat if you're watching this live. Either way. Anyway, let's go ahead and jump on into this. So first problem we're going to be going over here is we're going to take the integral of p to the fifth times natural log, or ln, of p dp. So I've already kind of mentioned that we're going to be going over integration by parts. Just real quickly to touch on kind of how you know that it's integration by parts. We pretty clearly have here the product of two different functions that we're integrating. That is typically going to be a pretty good sign that integration by parts would be a good option, or certainly at least considering using that to integrate whatever function you're dealing with. So since we have this product of two different functions, p to the fifth being one function and natural log of p being our other function, pretty good indication that integration by parts may be the best option. It may not, depends on what the function is, depends on the situation. There definitely are products like this where U substitution is the best option. But in this case, I think that integration by parts is going to be your best option. Where I did get this problem from, it did actually come from, the context was integration by parts. So in this case, that kind of gave it away. But if you wanted to think about how we know integration by parts is actually going to be the best option, just kind of where my brain goes when I look at this problem specifically, obviously the product is a big key. You need that in order to use integration by parts. But what makes me think that using integration by parts is going to work quite nicely in this case is the fact that one of those products, or one of those things that is a part of the product, is just natural log of our variable. The reason why I say that is, what is the derivative of natural log of p? Well, if we took the derivative of ln p, took the derivative of that, that would just give us 1 over p, which if we were to think about taking the integral of p to the fifth, that would give us some sort of p to the sixth term, right? Which if we have a p to the sixth times a 1 over p, that's going to end up simplifying quite nicely. And I'll show you kind of what I mean by that. But the point is just thinking about the derivative of one of our terms with the antiderivative of the other term being p to the 6 and 1 over p. If you multiply those together, which is what the integration by parts formula is going to get us to do, things should simplify quite nicely. So let's just start with the integration by parts formula first of all. Like I said, this formula is on my Calculus 2 study guide. So if you want to go grab that, there is a link down in the description where you can get more info on that. But integration by parts, the formula says that if we have the integral of u times dv, we can rewrite that as u times v minus the integral of v times du. So you can see that basically what we have in our original integral is these two things where we are kind of converting this into another integral, which the idea is that this integral should be easier to solve than this one. But where this integral comes from is it's going to be the product of the derivative of u, du is the derivative of u, and v is the antiderivative of dv. So basically, if you take the derivative of one of your terms and the integral of the other term, the product of those two things is going to be your new integral. So just kind of looking ahead a little bit, the integral of p to the 5th being some constant times p to the 6th, multiplying that by the derivative of ln p, which is 1 over p, those are going to simplify down into just a p to the 5th term, which should be pretty easy to integrate. We can do that just using the power rule. So let's see how this actually plays out. I did just want to kind of give you a hint of, kind of when I look at a problem, you want to kind of try and think a couple steps ahead. Kind of like chess in that way. You want to think a little bit ahead just to kind of see where the problem may be going. And of course, you don't have to be able to like solve everything in your head. That's not the point. The point is just to think a little bit ahead just to see if, one method is going to actually be helpful or, at least has a chance of being helpful, or if there's another method that you might want to consider instead. Of course, sometimes with math, unfortunately, you have to just kind of experiment, go down one path or another path and, get to a dead end and realize that path doesn't work. Kind of sucks and it kind of feels like a waste of time, but that's kind of part of that learning process. And as you start to do that more and more, you'll start to kind of recognize ahead of time in the future, I did a problem that looked kind of like this yesterday or something, and it got me to this dead end. So maybe I should try something else instead. And that's just kind of part of the process of learning math. But anyway, in this case, we have, with any integration by parts problem, the first thing you want to do is decide what's going to be your u and what's going to be your dv. So like I said, u is going to be the thing that we are going to take the derivative of. With ln p, the derivative of ln p is 1 over p. The derivative of ln of something is much, much simpler to deal with than the antiderivative of ln p, or ln of whatever our variable is. So generally, if you have natural log of your variable being one of your terms in an integration by parts problem, you probably want to take its derivative and make it u. Not necessarily always. You want to kind of consider what are your two options. Is the other one even harder to take the integral of? But if we look at our other term, in this case, p to the 5th, that's going to use power rule either way, whether we take the derivative or the integral of it. So in that case, it's actually not going to matter. P to the 5th is not going to be easier or harder if we make it dv or u. However, ln of p is going to be much easier to put as our u than it would be to put as our dv. Because what we also need to do, once we've kind of determined what our u and our dv are, is then figure out du and v. Well, like I said, du is just the derivative of u. The derivative of ln p is 1 over p, like I said. And v is always just going to be the antiderivative of whatever we said our dv is. So in this case, dv is p to the 5th. V is going to be the antiderivative of p to the 5th, which can be found using the power rule. Power rule just says we're going to raise our power by 1, so increase our power from 5 to 6, and then divide by our new power. Instead of dividing by 6, I'm instead going to multiply by 1/6. It's the exact same thing, just kind of is going to make things a little bit easier for us in the next step. And that's just another example of what I was saying earlier about just kind of having experience working through problems, being able to think ahead a little bit more. So let's go ahead and apply this formula over here now. So what we know is we had this original integral, which we could think of as u times dv. And we can now, after we've kind of figured out our u, dv, du, and v, we can use these 4 pieces and plug it into this formula to figure out what this original integral is equal to. And it should be equal to u times v, so ln of p times 1/6 p to the 6. I'm actually going to write it in the other order. So 1/6 p to the 6 times ln of p minus the integral of v times du. So minus the integral of 1/6 p to the 6 times du, which is 1 over p. And this is what I was getting at earlier about the derivative of ln p conveniently simplifying down with the antiderivative of p to the 5th, because now we have a p to the 6 times 1 over p. Well, this p is going to cancel with one of these p's, just turning it into the integral of 1/6 p to the 5th. So now this thing that we're integrating is something that can be integrated just using the power rule, instead of what we had before that could not just be done with the power rule. It required some additional tricks. Okay, so now what we've done is we've kind of simplified our original integral down into something else that just involves this simpler integral. And do keep in mind, we do want to still have a dp here. In fact, if you want to be kind of technically correct, we should have had a dp here and here as well. You will always put your dp, or whatever you had here, in this case it's dp, is going to go with our dv and our du. And then as a result, it ends up carrying into here as well. So now all we have to do, first of all, actually, let's think about this. We have this constant here. A constant, when you have a constant times a bunch of other stuff in an integral, the constant can be pulled out of the integral. So we can actually rewrite this as 1/6 times the integral of p to the 5th times dp, or not times dp, p to the 5th dp. And then over here, we'll still have all this stuff outside of the integral. So the nice stuff about all this stuff out here, it's already been integrated and dealt with. We still just have this integral here to deal with. So basically, that's just going to carry on down. And then to integrate p to the 5th, we again just have to apply power rule, which is just going to raise our power by 1. So raise the p to the 6th, and then divide by our new power, which is the same as multiplying by 1 over that new power. So then this is going to simplify down into 1/6 p to the 6 ln of p minus 1 over 36 p to the 6th. And we could simplify this a bit by pulling out a 1/6 p to the 6, because both terms have a 1/6 in common here that we could factor out, and they both have a p to the 6 here that we could factor out. So doing that is just going to give us 1/6 p to the 6, and then parentheses ln p minus 1/6. And now that's going to be, and then actually we do want to add a plus c on there as well. And then that's going to be the integral of the original function that we had to find the integral of. All right, so that's it for that first one. Not seeing any questions in the live chat. Not sure what that is. That might be a spam link that somebody put in there. Not sure how to get rid of that. I'll have to check into that later. Don't click on that link. All right. Anyway, let's go ahead and move on to the next problem. So now we're going to get into some examples of what it looks like to do integration by parts for a definite integral. So this is going to be very similar to what we just did in the last problem. In other words, very similar to using the integration by parts to find the integral of an indefinite integral, with just kind of one small kind of edit to the formula. And this formula is also on my integral calculus cheat sheet, or my calculus 2 study guide. Very similar formula with one main difference. So basically, what that formula tells us is if we have the integral from a to b of u times dv, this can be rewritten as u times v evaluated from a to b minus the integral from a to b of v du. So very similar formula. All we're really doing is just kind of evaluating between these bounds is really kind of the main difference. So again, same process that we normally want to do with integration by parts. First thing we need to do is figure out what we're going to make our u, what we're going to make our dv, then figure out what we're going to make, or what our du is based on the u we chose in the first step, and figure out v based on the dv we chose previously. So in this case, we can see that we have a dy over here. That tells us that y is our variable. That's kind of an unusual variable. Usually y represents a function, but in this case, since the dy is here, that tells us, that indicator tells us y is your variable. We're integrating with respect to y. So when we're looking at this, again, what do we want to take the derivative of? What do we want to take the antiderivative of? Well, before we do that, what I'm going to suggest is we need to kind of rewrite this in another form that makes integration by parts actually make sense. Because integration by parts requires that we have the product of two things, u times dv. Well, here we have a quotient. We have division instead of multiplication. However, what we can actually do is we can rewrite this function, ln of y divided by square root of y. We can rewrite, first of all, we can rewrite square root of y. So that's the first change I would suggest, is don't think of square root of y as the square root of y. Think of it as y to the 1/2 power, because y to the 1/2 power is exactly the same as square root of y, right? Taking the second root is the same as raising something to the 1/2 power. In general, if you have an nth root of something, you can rewrite it as that thing to the 1 over n power. That's always going to be the case. So in this case, that gives us y to the 1/2. Well, what you also want to consider is that when you are, or when you have a power, something raised up to a power on a denominator like this, you can move it up to the numerator by making the power negative. So ln of y divided by y to the positive 1/2 power is the same as ln of y times y to the negative 1/2 power. By making the power negative, we can move it up out of the denominator of the fraction, which is convenient because now we actually do have the product of two things. So now we can actually apply this integration by parts formula. So to do that, what we need to do, actually, I should leave that there, is, again, decide what's going to be our u, what's going to be our dv. Well, our u is generally the thing that's going to cause us, be easier to take the derivative of, or create a cleaner thing to take the derivative of. And dv is the thing that's going to create a cleaner thing to take the antiderivative of. Very similar to the last example we did, y raised up to some power is not going to really matter whether we take the derivative or the antiderivative. In either case, we're just going to apply power rule, and we're just going to end up with some constant times our variable raised up to some constant power in either case, whether we take the derivative or the antiderivative. However, ln of y is going to be much, much better to take the derivative of than it is to take the antiderivative of, because the derivative of ln of y, or ln of whatever you're taking the natural log of, is just 1 over that thing. So the du in these integration by parts problems is always just going to be the derivative of u. Well, if u is ln of y, du is just 1 over y. Okay. If ln of y is our u, then y, and actually I should have had a dy on here as well, y to the negative 1/2 dy is going to be our dv. So the dy is always going to carry in with the dv here, and then we also need a dy in our du term. So the du term and the dv term are always going to have dy, or d whatever your variable is. So then once we've decided that y to the negative 1/2 is dv, we need to find v by taking the antiderivative of y to the negative 1/2, or take the antiderivative of dv. Well, like I said, to take the antiderivative of y raised up to some constant power, we can just use the power rule. Power rule says we're going to keep our base the same, keep our base as y, raise our power by 1, or add 1 to our power. Negative 1/2 plus 1 is the same as negative 1/2 plus 2/2, right? We need to get a like denominator to add fractions. Negative 1/2 plus 2/2 is positive 1/2. So our new power is going to be positive 1/2. And then by the power rule for integration, we have to, after we raise our power by 1, we have to divide by our new power. Dividing by 1/2 is the same as multiplying by the reciprocal of 1/2, which is 2. So that's going to give us 2 times y to the 1/2. Okay, so now once we've found these 4 pieces here, we can plug those 4 pieces into our integration by parts formula. So we're going to get the integral from, a to b, 4 to 9 in this case, of u times dv, which we've said ln of y is u, y to the negative 1/2 is dv. We can rewrite this as the integral, or I'm sorry, u times v, so ln of y times 2y to the 1/2, evaluated from a to b, so from 4 to 9, minus the integral from 4 to 9 of v times du, which is 2y to the 1/2 times 1 over y. And then dy needs to be on there as well. Okay, so now what we've done is we've converted this original integral into one that should be easier to integrate. Before we do that, though, we probably want to simplify this. And that's a lot of times how these integration by parts problems are going to go, is reapplying this integration by parts formula to rewrite our original integral as another one. It's generally still going to be the product of two things, because that's what the formula says, right? It's just v times du instead of u times dv. But the hope is that the product of these two things can actually simplify. A lot of times that'll be in the form of something canceling, which in this case, let's think about how this could cancel or simplify. Having y to the 1/2 and then having a y on the denominator here, these two things are going to partially cancel out with each other. Y to the 1/2 divided by y, how that's going to cancel is it's going to basically subtract 1, because y is the same as y to the 1 power. It's going to subtract 1 from this power, right? If you have two terms, like let's say x to the a over x to the b, that would simplify to x to the a minus b. So in this case, since we have y to the 1/2 divided by y to the 1, that's going to simplify into y to the 1/2 minus 1, which is going to be y to the negative 1/2. And then we have this 2 out here. Well, if we have a constant multiplied by all the stuff we're integrating, we can pull the constant out of the integral. So the only thing we're integrating now is y to the negative 1/2 dy. We can pull our constant 2 out. The rest of this is going to stay exactly the same. And we're still going to evaluate this from 4 to 9. Okay, so now let's deal with this integral. All we're doing now is integrating y to the negative 1/2. Well, we already did that, actually. If you look back here, our dv was y to the negative 1/2 dy. So to integrate that, we found that it was 2 times y to the positive 1/2. So we actually know right off the bat, this is just 2y to the 1/2. And we do still have this 2 out here, right? It was 2 times that integral. We know the integral itself is equal to 2y to the 1/2. So we're going to have 2 times 2y to the negative 2y to the positive 1/2. I'm sorry. That's going to be minus. All this is going to stay the same. And now let's think about this. So here, this kind of vertical bar with 4 and 9 written here, all that's saying is evaluate this expression from 4 to 9. Well, what we're also going to have to do, thanks to the bounds of this integral, is evaluate this expression from 4 to 9. So basically what we're doing is we're evaluating the entire thing from 4 to 9. You could do them separately and then subtract them, or you could do them all together. It's really not going to make a difference. You're going to end up with the same number either way. But all that means to evaluate something from 4 to 9, from a lower bound to an upper bound, is you're going to plug in 9 into wherever you see a y. So we're going to get basically ln of 9 times 2 times 9 to the 1/2. 9 to the 1/2 is the same as the square root of 9. So the square root of 9 is 3. 2 times 3 is 6. So ln of 9 times 6 minus 2 times 2 is 4. 9 to the 1/2 is the square root of 9, which is 3. So 2 times 2 times 3 is 12. Okay, so this is what we got from plugging in 9, basically. All we did is just go to wherever we see a y, which is here, here, and here, and replace it with a 9. And doing that leaves us with ln of 9 times 6, all minus 12. Okay, then we need to minus whatever we get from plugging in 4 into all of our y's. So now go to all of our y's here and replace it with a 4. And then we're going to do basically all this from plugging in 9, all this from plugging in 4. It is very important that you need to make sure you put parentheses around your two pieces like that. And then once you figure out what the value of what's inside the parentheses here is, then you can deal with the fact that you're subtracting them. So now if we plug in 4 for all of our y's, we're going to get ln of 4 right here. 4 to the 1/2 is the same as square root of 4, which is 2. 2 times this 2 is 4. Minus 2 times 2 times the square root of 4, which is 2. So 2 times 2 times 2 is 8. Okay, so then we can simplify this. We would have 6 times natural log of 9 minus 12. This negative sign is going to distribute through the parentheses here. So we're going to get minus 4 natural log of 4 minus negative 8, which the negative and the negative will cancel, giving us plus 8. Then to simplify this a bit further, 6 natural log of 9 minus our 4 natural log of 4 over here, minus 12 plus 8 would be minus 4. And that should be about it. We could probably apply some log properties if we really wanted to simplify this further, but I think this is a perfectly fine answer. This will give us, you could just basically plug this into a calculator from this point fairly easily, or if you want to leave it in exact form, that is a perfectly sufficient answer. Like I said, you could simplify it down into a single log using different log properties, or at least you should be able to. I would need to look at that a bit more, but we'll go ahead and leave it there for the answer to that problem. So notice before you, kind of just accept that as the truth and move on, I want to point something very important out here. Look at the difference between the answer we got from this problem and the last one. So keep in mind, this problem, the second one we just did, was a definite integral, which all that means is it had bounds, right? It had bounds on the integral. That is what makes it a definite integral. What do you notice about this? There are no y's in it. There's no variable in this thing here. We just have 6 times ln of a number minus a number times ln of a number minus a number. This is all one big expression that we could plug into a calculator, and the calculator would return us a number, a one single number that is all equal to. So definite integrals give you a number when you're evaluating them. If you look back at the last problem we did, go back over here, our answer had p's in it. It had the variable that we started with, p. So your indefinite integral, when there's no bounds, which this one did not have any bounds on it, we go back up to the top here, there was no bounds. Indefinite integral is going to give you something with variables in it and a plus c, some unknown constant. Whereas your definite integral is going to give you a number. There's no variables in there because we had bounds on our initial integral. All right, and that's it for that problem. So we can go ahead and look on to the next one. Let me just take a peek here. See if there's any comments here. Don't think there's any questions. I do see some comments that look kind of spammy. Yeah, I'll try and see if I can remove those really quickly, or if that's something I can even do. Hang tight. Sorry, just 1 minute. All right, this doesn't seem to be. Okay, that seems to have worked, I think. All right. Anyway, let's go ahead and get into this problem now. So, not seeing any questions. Like I said, if you do have questions, feel free to drop them in the live chat. Happy to help address those as we go. But let's go ahead and get into this this example here. So again, let's just start with our integration by part. I'm going to go through this one a little bit quicker. You know, if you want a little bit more in-depth explanation, checking out the last two examples would be a good place to start. But we'll go through this one a little bit quicker. So we'll start with the formula. Again, this formula is on my integral calculus cheat sheet, my Calculus 2 study guide. Link is in the description or the pinned comment if you want to check that out. But the formula just says if we're taking the integral from a to b of u times dv, that can be rewritten as u times v evaluated from a to b minus the integral of v times du from a to b. So just like we've done with every integration by parts problem on my channel, first thing you want to start with right off the bat, figure out what you want to make your u, what you want to make your dv. So again, kind of similar to the last example, first thing we need to do here is rewrite this in a form that we can actually apply integration by parts, which is the product of two things. Because right now we have division, which is not really going to work. So what we want to do is think about how we can rewrite our denominator to move it up out of the denominator and to make it into a product of these two things. Well, just like the last example we did, if we make our power negative, we can do that. So if we make it y times e to the negative 2y, we can move the power up out of the denominator, or move the whole term up out of the denominator. So now we have the product of two things. So now we need to figure out what's our u, what's our dv. What's the thing that we want to integrate? What's the thing we want to take the derivative of? Well, in general, with integration by parts, if you have one of your two terms being an exponential like this, it's not really going to make a difference typically, as long as your power is just some constant times your variable, like in this case, e to a constant times y. It's not really going to make a difference if you integrate or differentiate that, because the integral and the derivative are both just going to be some constant times e to the negative 2y. So we don't really care which one we make that. However, y is going to be easier to take the derivative of, because if you think about the derivative of y versus the antiderivative, the derivative of y is just 1. If we're taking the derivative of y with respect to y, it's just 1. If we take the antiderivative of y, we're going to have to use the power rule, which is going to make it into a y squared times some constant. Y squared times some constant is clearly a little bit more complex than 1, just a constant number. Sorry, needed a little water there. So if we're going to make our y u, because that's going to allow us to take the derivative of y instead of the integral, that leaves e to the negative 2y for dv with our dy in there. So then once we figured out y and dv, we need to find du and v. Well, du is just the derivative of u, derivative of y, like I said, is 1. And we do also want to keep our dy in there. dy is always going to go with dv and du. And then the antiderivative of e to the negative 2y, you could kind of solve this out the long way. You know, the best way to actually prove that this is the integral would be to solve just this one little kind of sub problem with a u substitution. I'm going to skip through those steps and just tell you the antiderivative of this is going to be negative 1/2 e to the negative 2y. And just as a quick check, we can definitely confirm that that's the case just by thinking about if we were to take the derivative of this term here, would we get back to what we had here? Well, if we took the derivative of this term here, we would have to use chain rule. Chain rule says that we would take the derivative, the constant is just going to remain here, constant times a function. The derivative of a constant times a function is the same as that same constant times the derivative of the function. So this negative 1/2 will just carry through. If we take the derivative of e to the negative 2y, chain rule says we would take the derivative of the outside, which is e to the negative 2y. Well, the derivative of the outside would be like saying the derivative of e to the x. The derivative of e to the x is just e to the x. So the derivative of the outside doesn't actually change anything. Chain rule says derivative of the outside, leave the inside alone. So we leave our negative 2y as negative 2y, and then we multiply by the derivative of the inside. Multiplying by the derivative of the inside, the derivative of negative 2y is negative 2. And then we would still have a negative 1/2. Negative 1/2 times negative 2 will cancel out, leaving us with just e to the negative 2y. So that does indeed get us back to what we started with. Okay, so once we've decided our u, our dv, our du, and our v, we can plug these 4 things into this formula here. So doing that, we're going to be able to rewrite this original integral as u times v, so y times all this here. So I'll actually write the constant out front here. So negative 1/2 y e to the negative 2y. And that's going to be evaluated from a to b, from 0 to 1. And then minus the integral from 0 to 1 of v times du. So v times du, which is just 1. So basically just all this. Negative 1/2 e to the negative 2y dy. Okay, so then let's just leave all this stuff out here. What's outside of the integral we'll just leave alone for now. We'll deal with that in a minute. Then what we can do here, let's just kind of simplify this integral here. First of all, we have a constant which we can pull out. If we pull out this constant, pulling out a negative 1/2, the negative from here is going to cancel with that negative there, giving us plus 1/2 times the integral from 0 to 1 of e to the negative 2y dy. So now what we've done is we've applied this integration by parts formula to kind of rewrite this original integral in a form that just requires us to find the integral of e to the negative 2y dy. Well, we already know what the integral of e to the negative 2y dy is. We found it right here. We know that the integral of that is negative 1/2 e to the negative 2y. So now we can replace this with negative 1/2 e to the negative 2y. So doing that is just going to give us 1/2 times negative 1/2 e to the negative 2y here. And keep in mind, this is still going to be evaluated from 0 to 1 because we still have our bounds on our integral here. And then all this is going to remain the same. We haven't done anything that would change any of this at this point. Okay, so keep in mind what we have here. We have these, again, these two separate parts that are each being evaluated from 0 to 1, 0 to 1. So what we can do is we can kind of simplify that down into one single thing and evaluate the whole thing from 0 to 1. So basically this part here is just right here. And then we have this part here. The 1/2, the positive 1/2 times negative 1/2 is actually going to give us negative 1/4. And then e to the negative 2y. And this whole thing, we need parentheses around the whole thing now, is being evaluated from 0 to 1 because each half before was being evaluated from 0 to 1. We can combine that. If you play it out step by step, you would find that you'd get the exact same number. So now all we have to do to evaluate this from 0 to 1 is first plug in our upper bound. So just go into our equation here, and wherever we see our variable, which is y, we're going to replace it with our upper bound. So negative 1/2 times 1 e to the negative 2 times 1 minus 1/4 e to the negative 2 times 1. Okay, so that's what we get just from plugging in our upper bound. Now it is very important. You need to put parentheses around this whole thing. And then what we're going to do is then go into this whole thing again and replace all of our y's with our lower bound. So this is what we get evaluating at 1. Now we need to do the same thing with our lower bound of 0. And then what we're going to do is we're going to subtract the 2. So negative 1/2 times 0 times e to the negative 2 times 0 minus 1/4 e to the negative 2 times 0. And again, put parentheses around each half. Whatever you get from plugging in your upper bound needs to be all in parentheses together. Whatever you get from plugging in your lower bound needs to be all in parentheses together. And then you subtract the two different halves. So I'm not going to go through actually solving it from here. I'll just leave it at this point. But you definitely should go ahead, get that practice, see what you'd get of, basically plugging in all this. At this point, we just have one giant expression, which can just be plugged into a calculator. You could go through kind of piece by piece and figure out what each of these pieces are equal to. But at the end, once this is all simplified down, it's just going to be some number. If you want to leave it in exact form, you're still going to have these e's in here because that is a very specific exact number, kind of like pi. But in either case, our answer here is a number, which is what happens whenever you evaluate a definite integral, which is one that has the bounds on here like that. All right, I'm not seeing any questions here. So we'll go ahead and wrap things up here. Like I said, these formulas are all in my integral calculus cheat sheet, Calculus 2 study guide. If you want to check that out, there's a link down in the description where you can go get that. It is available for instant download, and I think you'll find it very helpful as you work through integral calculus. So go check that out. If you got some use out of this video, please be sure to hit that like button as well. That'd be a huge help to me and my channel so I can keep making more videos like this, and so we can keep growing the Jake's Math Lessons community and helping everybody get better grades in calculus. Thanks, and see you next time. See you next week. See you whenever. Have a good rest of your night. Good Valentine's Day.